Dear students, today I am talking about the stereochemistry of disubstituted cyclohexanes. So, under this, we already completed the one disubstituted cyclohexane. Now, in 1,2 disubstituted cyclohexane, in previous videos, I have already completed 1,2 dimethyl cyclohexane. Now, in this video, I am going to talk about 1,3 dimethyl cyclohexane. Among that, cis-1,3 dimethyl cyclohexane I already completed in previous video. Now today I am going to talk about the trans-1,3 dimethyl cyclohexane. Now this is the trans-1,3 dimethyl cyclohexane. Now this is the planar structure of the cyclohexane. First, always remember whenever the compound is given trans-1,3 dimethyl cyclohexane, first you draw this in a planar conformation, that is planar hexagon. After this, you number it 1, 2, 3, 4, 5, 6. Then select the number where you have to write down the substrate. So 1 and 3 carbon you have to select. So this is number 1 carbon and number 3 carbon where you have to write down the methyl group. Now next one is what? The geometry, trans. So trans means one is up, one is down. So here, this methyl group at one position is going in upper direction, that is wedge bond, and a third position going in a downward direction, that is a dotted bond. So trans is the geometry of this two methyl group is opposite. So this is the one way of representation. But it's another way of representation. Either instead of writing the C1CH3 is wedged, now I can draw C1CH3 in dotted bond and C3CH3 in wedged bond. So these are the two possibilities. Now I draw this into a chair conformer. Now when you are going to draw this in a chair conformer, so you always remember how to draw the chair. First you always draw this 5-6 bond and 3-2 bond. These two parallel lines we have to draw first of all. And then once you complete these two parallel lines, then you complete the upper part of the chair, that is the head of the chair, and the lower part of the chair. So I call this as the tail of the chair. So number 1 carbon is the head of the chair. So once you draw the chair, then your duty is to write down the number to the carbons. So C1 is 2, 3, 4, 5, 6. Now what is the requirement at the one position? At one position, the methyl group you have to show in upper direction. So this is the upper directed bond and this one is the lower directed bond. So where you have to place the methyl group? The placement of methyl group at the beta position, that is the wedge bond. Hence, this bond is now axial. Why this bond is axial? Because this is in the plane of the chair. The bond which are in the plane of the chair, that bonds are called as a axial bond. That means they are perpendicular to the chair. And the bond which are on the periphery of the chair, so this hydrogen now on the periphery of the chair, therefore this bond is called as a equatorial bond. So at number 1 position, the bond is axial or the substituent is axial. Now at number 3, what is the requirement at number 3? The methyl group is going in the downward direction. So methyl group going in the downward direction, always remember this group we have to always draw in parallel with this line. So this methyl group at number 3 position has to be parallel with this line. After this, next your duty is to write down the name of this conformer. At C1CH3, as it is an axial, so this group is axial. So I place axial for this. At number 3 position, now this group is equatorial. So I'll write here. So what is the name of this conformer? This is EE conformer. Again, one more thing you always remember. Once you draw a one chair, don't forget to write down the flip structure of this chair. Now, so for this, you write on the flip arrow. This is the flip arrow. Now here, this is the ball and stick model of the trans 1,3 dimethyl cyclohexane. This is number 1 carbon. This is number 2 carbon. This one is number 3 carbon. Number 1 is at the head of the chair, which is axial group. So this is the axial methyl group. Number 3, this equatorial group is going in downward direction. So this is equatorial group, or I call it is a alpha carbon, and this one is the beta methyl group. Now after flipping, what are the changes you observed? After flipping, the number 1 position going in the downward direction, number 4 position in upward direction. So number 1 is at lower direction, number 4 is at the top direction. Now due to flipping, the axial methyl group changes to equatorial. So this is the equatorial, and this equatorial methyl group at C3 position, it changes to axial. So this is now axial. So after flipping, axial methyl changes to equatorial methyl group, equatorial methyl group changes to axial methyl group. But the beta remains beta and alpha remains alpha. So this is the ball and stick model of the same. Now the name of this conformer is equatorial axial. Now look at this model. This number 1 carbon, number 2 carbon, and number 3 carbon. In number 3 carbon, now the bond is axial, but it is still going in a downward direction. So this bond is axial methyl group. At number 1 position, this bond is at the periphery of the ring chair. So this is an equatorial bond, but it is going in a upper direction. So we call it is a beta. Now in each structure, there is one axial bond and one equatorial bond. So what about the equilibrium arrow? It has to be facing in the same direction. So both the structure, that is AE structure and EA structure, they are equally populated. Both the structures are exist indicating AA conformer get flip into EA conformer. So both have the same energy. Now let us go with the energy calculation. Now in energy calculation, so you can see that is C1CH3 group is axial. So C1CH3 group is axial. So for that, if one axial group is there, then there is presence of Butin-Gauch interaction. So which two Butin-Gauch interactions are present? That C1CH3 group causing a interaction with C5 axial hydrogen. This is first interaction. And which is the another interaction? That is C3 axial hydrogen causing interaction with the C1CH3 group. They're coming within the water wall area, hence it causing the interaction. Therefore, there is presence of two Butin-Gauch interactions. So each interaction is found 0.9. Therefore, the total energy of this molecule is C1CH3 is axial, so 2 Butin-Gauch interaction, so that is 1.8 kilocalorie per mole. C3CH3 is equatorial, so no Butin-Gauch interaction, that energy is 0. C1CH3 and C3CH3, what type of relation is there? There is a 1,3 AE and 1,3 AE, one position axial group, third position equatorial group. Now you can see they are far away from each other, therefore they never interact. So this and this group never interact with each other, hence the energy is also 0. So total energy of this molecule is 1.8 kilocalorie per mole. Now the optical activity of this molecule. For the optical activity, what are the requirements? The three conditions. If it fulfills the three conditions, then what we have to say, that compound is optically active. What is the first condition? The compound should have the asymmetric center or presence of a chiral center. So Is there presence of a chiral center? The answer is yes. Which are those? C1 and C3. These are the two chiral centers present in this molecule. So the first condition it fulfills, presence of a chiral center. Now the second condition is what? There is absence of, now there is no symmetry element. That is the axis of symmetry or the plane of symmetry. Both the symmetry elements are absent. What is the third condition? Whether the compound is resolvable or not. Now here the compound is resolvable. The reason over here is, you can see now in this ball and stick model, what you see here, there is absence of any symmetry element. So you can see, you can pass the plane from any of the direction, as one group is going in downward direction, one group is going in upward direction. So there is a absence of symmetry. Because of the absence of symmetry, due to that the compound is optically active. So compound exists in a resolvable DL pair. For this, again, I request you to refer the book Stereochemistry of Ellil.